Good?
Okay, it's nice. Okay, okay,
Wow.
please. Time is yours.
Thank you. Thank you very much for this nice introduction, and also for inviting me to give this presentation during your workshop. That's really my pleasure. Today I'm going to talk about diamonds. So I'm going to introduce you to diamond facility. I will also give an overview of the techniques. There's quite a big range of techniques we have available, but I will just focus on key ones which are used for the materials characterization. And then I will also give you an overview of certain industrial experiments which were carried out at Diamond on various materials. So here we are. We are based in Oxfordshire, which is on the campus of Harvard campus. And there are also other research facilities around. So this is Diamond. We have ICIS. There is a central laser facility, the Medical Research Council, and also European Space Agency. The campus is expanding. There is more and more facilities which are establishing their facilities and offices there. This is a quite attractive location because that really helps in collaboration and getting access to the advanced characterization techniques in various facilities. So we are the national facility. We are funded through government in 86%, and the 14% is given by Wellcome Trust. This is the biomedical charity. And just to give you an overview, I'm not sure what the experience is in audience, so forgive me if I'm going into details. But just to start, how the synchrotron light is formed at Diamond. So we have 3 particle accelerators. Can you see my, just a question, can you see my mouse, or I maybe better find the laser?
Can you find the laser? You just, yeah, find in the corner. Yeah, you just click the.
I think I covered it up. On the top corner, or?
The right of mouse.
Yeah.
The right mouse, and
you move the mouse and then see.
Okay.
Yeah. Okay. Push the laser. No. Not here. No. This is. Okay. Can you go to the corner?
Okay. Click again.
Click. You click. You click the mouse. You click the mouse.
The right part. Normally. Oh yeah. Maybe. Oh yeah. I don't know why it's not coming.
Apologies, Dr.
It's difficult. Okay,
the laser.
Okay. You can
see your mouse.
Yeah, but you can use the mouse. It's okay. Okay, no problem.
Can you see that?
You can use the mouse, yeah.
Yeah,
we can see the mouse.
Yeah, we see your cursor.
Okay, sorry, I just cannot work it out.
The cursor of the mouse, yeah.
Announce? Maybe just. No, I don't really know where that could be. So just coming back to my slides. So Diamond machines are divided into 3 particle accelerators. So there is LINAC, booster, and then storage ring. So first, the electrons are ejected from the electron gun into the LINAC. And once they reach the energy of 100 mega electron volts, then the electron's band is transferred into the booster synchrotron. And the curve path is defined by the dipole bending magnets. And then they reach energy of 3 giga electron volts at Diamond, nearly speed of light. And once they are with the right parameters, they are transferred into the storage ring. And then from the storage ring, they go straight to the straight section to the beamline. Okay. So what you can see here is, so this is just one of the example of the beamlines, the model of it, where each of the beamline is divided into 3 sections. There is optic hatch, where there is a set of mirrors and the monochromators, which gives the right conditions to the beam, experimental hatch, where the users are allowed to set up their experiments, and just when they are ready to go, everything is controlled from the control room. Diamond started its operation in 2007. We, at that point, had only 7 beamlines fully operational, and gradually there was more beamlines built. There was 3 phases, and by 2018 there was 33 fully operational stations at Diamond. And each of them is very unique. So we have, for example, here, this is the high resolution powder diffraction beamline, where there is a massive high resolution diffractometer. There is a robot which transfers the samples from the carousel into the diffractometer. Or there is one of the spectroscopy beamline, where we set up the reaction cell, and there is no such a massive instrumentation present. So that's quite important, that each of the facilities we've got, it's quite unique in the instrumentations and also techniques which is available to use. So with Diamond, as I said, 33 stations, they are all grouped into science divisions. We have currently 8 of them, which involves, so that's macromolecular crystallography, structures and surfaces. We have imaging and biological group, magnetic materials group, big group of spectroscopy, imaging and microscopy, and soft condensed matter. And along of the beamlines, we also have other facilities which supports research on the campus. So that is the membrane protein laboratory. We also have UK X-ray free electron laser, and this is a hub, which means we really don't have free electron laser facility in the country, but there is a group which supports the research in this area and helps getting access elsewhere. Usually this is the European source in Hamburg. We also have XCAM facility, which is dedicated for fragment-based screening. I will talk more about it at the end of my presentation. And also we have a big center for microscope. Because of a high demand, we currently have 9 cryo microscopes on the campus, which is also part of Diamond facility, and they are all dedicated to life science. And we have 2 microscopes for physical science. Around 90% of work carried out at Diamond is undertaken under the peer review proposals, so all the academic and research facilities groups who are willing to use the facility. However, 10% of time is dedicated for industrial access, for the commercial work. So this is the group I'm working along with my colleagues. And this is just a few examples of the industrial experiment and the industrial problems which were solved in the facility. So starting off with pharmaceutical sector, Heptares, for example, they were looking into designing a new drug for the Parkinson's disease. GlaxoSmithKline was using one of our diffraction beamline to control the manufacturing process for the drug development. Our big catalysis company, Johnson Matthey, was looking at the speciation of platinum in the 3-way catalyst. Infinium, this is the oil-based company. They were trying to understand the crystallization process in biofuels. Unilever, the consumer product company, was looking at the microstructure of the shampoo. And Rolls-Royce was studying the stress strain impact on the fan blade. I will talk more about some of these examples later in my presentation. So I'm going to focus only on 4 techniques, which are at the core measurements to study materials. There is obviously quite a lot of others, specific techniques, and I would really need much more time to cover everything. So I will just focus on spectroscopy, diffraction, small angular X-ray scattering, and imaging. So each of these techniques provides different information. And also there is a nice overlap when we think about the length scale of the samples they study. So spectroscopy, specifically X-ray absorption spectroscopy, we look at the local structure. So we are talking about atomic resolution, diffraction. When we deal with small molecules, again, atomic resolution, but on the large molecules, we can go up to nanometers. And then scattering is probing the sample from nanometer to micrometers. And then imaging, the standard imaging measurement will look at the length scale of millimeters in the sample. However, we can't forget about very specific X-ray imaging techniques where we can probe the sample with the resolution of nanometers. So X-ray absorption spectroscopy, this is a technique I'm specialized at Diamond, and this is element sensitive method. What I mean by that is that if we select an atom of chromium, we can probe the elements around it, so all the neighboring atoms. We can probe the distance between them and also how many of those neighboring atoms we have present. We also can study the geometry and oxidation state of the selected element. So the list is quite extensive, and this is just an example of the data showing the chromium +6 and +3. And you can appreciate how sensitive the measurement is to oxidation state, but geometry and general local structure. So the pH feature, which is pronounced quite distinctly for chromium +6, this is telling us about the symmetry of the studied element. So the higher the intensity of the pH is, the more distorted symmetry. Then we can also look at the white line intensity. So this is where the absorption jump is taking place. There is a quite big difference between these two oxides with their intensities, and overall the Xane's features look very different. So in the simplest measurement, what we are doing is, and specifically we really want to study the Xanes, is we perform the measurement on a sample, and then we have a range of references which are measured and then compared to the studied sample. And that really is the simplest way of fingerprinting. There is much more advanced possibility to study this region using the modeling and advanced calculations, but this is still quite complex and still under investigations. So there's quite a lot of information in Xanes, and EXAFS, we apply analysis to look at the local structure, to look at the single scattering between the central atom and the neighbors. So in this typical measurement, we have the wide beam from the source, we have a monochromator which selects the right energy, and then we have the ionization chambers for transmission measurements. So we have I0 and IT after the sample, and then we can just using the logarithmic function, we get absorption. However, on samples which are autophic, that the X-rays won't pass through, or we have very little concentration of studied element, or samples is in general very complex, we use the fluorescence detector. And that gives a bit more information on the surface of the studied sample. So here is just, I wanted to show you the quite extensive list of elements which we can study. It's almost every single element in the periodic table, which can be studied by X-ray absorption spectroscopy. And the beauty of that measurement is that we can study the sample under any form and shape. So the sample could be in the gas phase, we could deal with liquid, solid, or we could deal with the multiple phase system. And this is one of the case studies which I would like to present to you. Right. So I have two case studies which are prepared where the X-ray absorption spectroscopy is used for industrially relevant systems and processes. The first one, it was based on collaboration between Infinium and University of Leeds. and diamond. So Sinuan was a postdoc with us for a period of 3 years. And the main scope of that project was to study the early stages of nucleation of calcium carbonate. And this very simple molecule still is not completely understood, but and it's quite desired by a range of different industrial sectors, which will involve pharmaceuticals, fuel additives, and catalysis. What we really wanted to achieve is to be able to study this nucleation under in situ conditions. Therefore, we had to be sure that we can accommodate the multi-phase system of gas, where CO2 is introduced, liquid, where the calcium hydroxide is dissolved in water or other solvent, and the solid, which is our product. So the first step was to build a custom the liquid jet cell, which could be used on the beamline. So this is just the schematics, where the chamber is specifically built for that purpose. We have the windows on both sides to allow X-rays come in and out. We also have a possibility to introduce the gases, which is a key part of the setup. And this blue line, this is the capillary. This is our liquid jet main component, which is connected to the reaction cell. With this cell, we were able to carry out a measurement using 3 different detection modes. So we could probe the sample using total electron yield, and that provides us very surface sensitive information. In the sample, we can penetrate the sample down to 100 angstroms. And then we could also perform the measurement in fluorescence. So we also had an additional window for fluorescence, where we can still perform surface measurement, but the penetration is much higher than in transmission, and also transmission detection mode, where we were all getting a bulk information on the sample. So this is just how it looks like. So the schematics I showed on my previous slide, this is basically this very tiny, small liquid jet. And then there was quite a lot of big infrastructure coming with it, where all the chemistry was happening. So we have the vessel where there is a reaction cell. We have the temperature control, but also the gas delivery into the reactor. And the peristaltic pump, which drives the flow of the liquid or the products into the liquid jet. And also we were it was very important for us to study what's happening inside the vessel. That's why we had the middle infrared probe introduced to the cell, which helped to have more information on the overall reaction. And this is just the magnified image of the liquid jet. You can see the capillary. So that was the quartz capillary, a very little stream of our system, multiple phase system. And then we have the X-rays coming from your right. And the fun is just collecting. So is our sample is in continuous circulation. There are many reasons for that. One of them, of course, is to be able to see if there is progress in the reaction itself, but also because we are dealing with the liquid, there is a higher possibility of the beam damage. So since we never really expose STEM particles to X-rays, that prevents also that issue. So what we could see here on our left, this is the Xanes data at calcium KH. So this is also quite important to notice that we are dealing with quite low energy. Therefore, we couldn't really put very robust and thick windows because X-rays wouldn't simply pass through. And at the start of the reaction, we can only see dissolved calcium hydroxide dispersion. And then within the first 30 minutes of the reaction, we can see successfully the formation of calcite. So that's quite pronounced. And then we can also look at the data, how they change in time. So we're looking at the proportions of each of calcium form present at specific point in the reaction. So at the beginning, we only have a calcium hydroxide dispersion with calcium ion. And while CO2 is introduced to the system, what we can observe is that, yes, there is some formation of calcite from the beginning, but at the same time, we have increased amount of calcium ions in the system before they're converted fully into the calcium higher calcite system. So that was quite interesting outcome from that experiment. We were able to successfully build the reaction cell, but also perform the multiple phase reaction and study the carbonation. And the Infineum company who was part of this collaboration got very big insight into the additives they use for the product development. So the second case study was based on collaboration between LIPI, so this is the Indonesian Institute of Science, and ICES Neutron Source, and the project was funded by a Newton Fund. And Ferenza was working with us at Diamond, just to point that he's wearing a thick jacket, and I think this was the first thing he had to do while coming to UK, to be equipped with a nice warm clothing. So just to give you a bit of background about the project. So the fresh fruit bunch is already now used for the production of biofuels. However, it was important to find something which is more sustainable. So empty fruit bunch were quite a big, showed quite a big potential to be used to first be converted to the bio-oil using the fast pyrolysis, and then applying the catalysis, bio-oil could be converted into the biofuel where the excess of oxygen could be removed. So that was quite an interesting approach, and the group at LIPI, they developed a catalyst based on nickel moly on bentonite, which could allow this conversion of the bio into the biofuel. And they were really interested in studying molybdenum KH and nickel KH, so study what's happening with the speciation of these elements in catalyst during the oxidation and also during the activation conditions. So X-ray absorption spectroscopy seemed like the best technique approach to study the chemical speciation. So we performed the experiment on the tin. So this is the same beam as the work carried out on multi-phase system. So here we have the capillary, quartz capillary, where the powder is loaded. So the catalyst is in the form of the powder. We have the gases delivered into the capillary. The temperature is controlled by the hot air blower. And then from our right to left, there is X-rays passing through the system. So we were able to measure the sample while we applied the different conditions of the activation. And the activation was based on introducing H2S at a higher temperature. So this is also the reaction cell, which is magnified. So that's the capillary, quartz capillary with the hot heating beneath. So we also performed, so while we were applying these conditions, we first carried on work on molybdenum, and then we repeat exactly the same reaction on nickel. And what we found out is, so on the left, this is the data Fourier transform of the EXAFs, and this plot, roughly speaking, Fourier transform gives us the radial distribution. So the maxima of the peak and the position can give us information straight from the beginning of while we receive the data during the measurement, that if we are dealing with the peak at around 2 angstroms, that will indicate us that our central atom, which we look moly in this case, and the neighboring atoms is around 2 angstrom distance from each other. The data is not phase corrected here, that's why it's really like 1.5, but once the data will be phase corrected, that will be around 2 angstrom. So this is the experimental data. And Ferenza also done quite a lot of computational simulations. So using the DFT calculation to first find the suitable models, which then they could be used into the fitting of the experimental data. And what we can see is that while molybdenum is converted from nickel moly oxide into the molybdenum sulfide, that's just a direct conversion from one form of an oxide to sulfide, because the distance between moly and the neighboring atoms increased. There is nothing in between. We also done the work on nickel, and that the situation looks a little bit different. So from the oxide of nickel moly, there is a transition, that like intermediate phase present, where we are dealing with nickel sulfide, nickel oxide, until eventually we have the oxide form present. So having the theoretical calculation was critical to find the right models and identify the species of these two elements of moly and nickel. So the work has been very successful. We were able to carry out the in situ experiment where both moly and nickel species were studied. We were only looking at the activation. However, the group was also working with Stuart Parker on catalytic process. So there was a catalysis studies done on a conversion of glycol into the phenol using the inelastic neutron scattering. Right. So the second technique I would like to talk about is X-ray diffraction. I'm sure most of you are familiar with the techniques. I'm not really going to go into the details. Just very briefly, once the sample is exposed to the X-rays, we get the diffraction pattern into data, and then that could be converted into the one dimension of diffraction pattern. And applying advanced structural refinement, we can then get the structure of the studied element. I have two case studies where industry used the diamond and specifically X-ray diffraction technique to solve their industrial problems. The first one is work carried out by Rolls-Royce. So they wanted to use diffraction to study what is the effectiveness of the surface treatment. So here we have the fan plate and the root of the fan plate. So that's more or less where I'm pointing. Is mechanically attached. So while the fan plate is rotating during the engine operation, that puts quite a lot of load onto the root of the fan blade. So it was very important for them to understand if the surface treatment they apply is efficient to prevent any crack formation or the propagation. They needed really to use the tool, which is first has very high resolution, but also it's non-destructive, where they don't have to cut their specimen into small pieces, because that will also impact the sample itself. And they also needed to use the tools and the facility where they can put the whole fan blade in one go. So just in somewhere where it's suitable to pull the large samples. So here is this the experimental heart of I-12. This is the engineering beamline at diamond. And that's where the fan plate is already aligned for the measurement. This is the experimental hatch, which can accommodate a sample 1 meter tall and the weight of 2 tons. And they applied the high resolution edge dispersive X-ray diffraction to look at the stress and strain impact. So that work was very successful. They were able to see which surface treatment is doing their job, that it maintains the good integrity of the fan. So that was using the getting information on the stress of the studied sample. And really it helped them to find the right surface treatment, but also reduce the cost of overall product. The second case study was the work led by Infinium. So this is the oil-based company, and they are looking into development of the fuel additives, because the fuel additives, they play quite a critical role in the nucleation and crystal growth in the biofuel when they are very cold temperatures are applied. So they wanted to understand the structure of it, and they used three techniques. This was the small angle X-ray scattering, but also powder diffraction and small molecule diffraction in order to study the nucleation by Sachs, but also to study the structure of the wax crystals during the cooling of the fuel. So they were able to perform the in situ measurement on the powder crystalline form of the sample. So that work was very successful. They were able to identify the conditions where the crystallization is happening, and they could also study a range of different additives and see how they perform. And so the next technique I would like to talk about is small angular X-ray scattering. So this is the technique which the contrast arises from the electron density difference between the particle and the media which surrounds it. We can get information on the particle size. We can get information on the particle size distribution if we are dealing with the same shape of the particles. We can also perform the particle shape analysis. And for the system where it's non-isometric, we can also study the particle orientation and alignment. So this is the typical setup for the experiment. You can just see it from here, where we have the sample is positioned at this end and detector quite far away. So we have the monochromatic beam, focus on the sample, and then distance of the Sachs detector will very much depend on the range of the particle size we want to study. So when we want to deal with very, very small particle size, we will increase the distance between sample and the detector. The measurement itself is very fast. We can obtain data in milliseconds. Setup is a little bit complex. It requires usually a few hours, and especially if we need to change the distance of the detector. We can probe a sample from 1 to a few couple of thousand of angstroms. And what is quite important is that along with the Sachs measurement, we can also perform wax, which in other words is X-ray diffraction. So there is a wide range of sample environment available for that on that beamline, where we can apply different temperature, pressure, we can introduce different gases and study it in situ. I have a couple of case studies where the industry uses Sachs to solve their industrial problem. So Hewlett-Packard company wanted to study the dispersion of the pigment in the liquid crystal media. And specifically, they wanted to know what is the behavior of the suspension when it's exposed to or different electric field is applied. So they wanted to have a technique which they can study suspension, and also they can perform very fast measurement. So Sachs seemed like the best technique which could help them to obtain this information. And once experiment was complete, the customers had enough information to choose the suitable product for further development. The second case study is dedicated to consumer product samples, and this is not really industrial partner. This is the University of Bath scientists. They were very interested. They've seen the potential of using the cellulose waste into the cleaning products. So it looked, so the cellulose waste had very promising properties of the thickening in the formulation. However, it was the behavior of gelatin wasn't really completely understood. So they used small angle X-ray scattering, where they studied this sample under different conditions. So we're using different salt concentration, different type of concentration, and also using different pH level or surfactants. The results were very useful for them, and that helped them and opened the avenue of any other sustainable resources which could be applied in the formulation compounds. Right. So the last technique I would like to focus on is X-ray imaging and X-ray tomography. We can obtain the radiography. So this is the 2D representation of the sample, basically the phase contrast, or we can have the 3D construction of a sample when the sample is rotated during the measurement. So what we have here is the representative sample of like a injector, and then the projections are collected at every angle from 0 to 180 degrees. That will give us, that's more or less what we get. It just looks, it doesn't really provide much information if we see look at the sample in 2 dimensions. But then if we just use one of the planes of the sample across, we get the sinogram, and then applying the random transformation, we obtain the tomogram. So we can really study the sample and get the complex information on the internal structure. Just to give you a bit more realistic example, so when we want to study a fly as a whole, we rotate a fly from 0 to 180 degrees, and we obtain the images. You can see they are just all the orientations. And once we complete this measurement, we just choose one of the planes, and the phase contrast of that plane will give us a sinogram from 0 to 180 degrees, and the transformation will obtain the tomogram. And if we stack all the tomograms on the top of each other, we have a 3D representation of our specimen, and also we can look what's happening inside of the sample which is studied. I have one case studies where the industrial company, pharmaceutical company Pfizer, used X-ray imaging to solve their problem. They were, so this company were very much interested in studying the porosity of the beads. So this is the drug, which is in the form of the beads. And they wanted to understand the layering process. Because what they discovered is that different batches of the sample was giving a different release rate of the drug. So they just wanted to find this correlation. And so this was the sugar-based inert chorus, which went undergone through different drug layering. And then once it was in the final product, we used X-ray imaging on various beads from different batches. And that helped scientists to find a correlation between the porosity and the release rate of the drug. This was a very useful experiment and provided lots of information on the product formation. And also that helped scientists to find the best way to be more consistent in the formation of the beads, but also to have a bit more control over it. And also I would like to highlight one of the facility which we have available at Diamond. This is the long duration experiment beamline. This beamline is attached to our high resolution powder diffraction. And what you can see here on this image, they are all rays. And at each of these rays, there is a sample environment which can accommodate specific conditions So we can, for example, have furnaces which heat the sample to very high temperatures. We can have the battery system, which can do charging, discharging for extended period of time. We can have some concrete materials and which undergoes under different hydration conditions, or pharmaceutical compounds under different humidity conditions. So this is just a few examples. And the idea is to store the reaction in situ for a period from few months up to couple of years, and then perform the X-ray diffraction measurement just once a week. So for this extended period of time, that gives very important information for scientists to see the deactivation of the specific material or behavior of during the charging, discharging. So this beamline has been performing very well. There was quite a lot of successful experiment carried out just until the COVID started. Then there was some issues with the instrumentation. And just now, the scientists preparing new systems, new reaction cells to restart the long block of experiments. So just to show you a little video, it's quite fast, but you can see what's happening, that there is a diffraction detector, which then motor brings a specific sample environment. Usually there is a few of the sample environments loaded in each of the rails, which apply different conditions or exactly the same. And that measurement will only be performed once a week. So that just improves the efficiency of this measurement, just when we can use the motor. And we had quite a successful collaboration between Rolls-Royce and Leica and University of Cambridge, where they were interested in the alloy aging using the Lincoln cells. And just at the end, I would like to finish on to tell you that we have quite a lot of research going on COVID-19. So since the pandemic started, obviously all the world has been affected, and Diamond has never stayed still. They were working very hard on, so I'm saying they, it's really my colleagues who are working the life science. They work very hard on trying to understand the virus and also find the suitable drugs to treat the COVID-19 patients. The initial scope was to work on the antibodies, which are formed from or received from llama, the animal, and that antibodies show promising results to treat the SARS-CoV-2 molecules. So that was just the beginning. The drug hasn't been discovered, but quite a lot of useful information has been obtained. And here is just to show you the scale of the work undertaken in the last couple of years. The main work is done using XChem. So this is our fragment X-ray crystallography screening platform, where we can introduce protein to hundreds or thousands of different compounds. And doing that in the efficient way, we can find hits in much more quicker way than doing individual experiments. So what I mean by hits, every hit, this is the binding site found between the protein and the compound. And the compound could eventually lead to the drug development. So originally scientists look at the main protease, and already early year of 2020, they screened over 1,000 fragments and they found 74 hits. Since then, there were many more fragments identified, and until now, there was around 22,000 data sets collected across 20 projects. And this doesn't really include any of the industrial work we do in our facility. So the work is still ongoing, and currently there is a consortium formed called COVID Moonshot, and that brings together around 30 groups from different parts of the world, from United Kingdom, United States, India, and other European countries. And the main scope of this group is really to find the antiviral drug for COVID. And recently they got a funding of £8 million to carry on research in this area. So with that, I would like to thank you, and please do ask any questions if you have.